Today's topic is channel state information. The algorithms used for Mimo systems can be classified based on the amount of channel state information that they require. So the classification is, first classification is full channel state information at the transmitter and also at the receiver. So the first classification of the algorithm used for Mimo is full channel state information at transmitter and full channel state information at the receiver. It is an ideal case. So practically this is not possible because it is very difficult. So it is an ideal case and it can achieve highest possible capacity among all the possible categories. This is the case which can achieve highest possible capacity. Second one is average CSI channel state information at the transmitter and full CSI channel state information at receiver. So the second case, average channel state information at transmitter and full channel state information at the receiver, is easy when compared to the first case. First case is difficult, whereas the second case is easier when compared to the first case. And this is easier when compared to this, but it requires a slow feedback or it requires calibration for the reciprocity. So in this case, both the receiver and transmitter knows the channel perfectly. It has the full information about the channel, and also the instantaneous channel conditions is known for both transmitter and receiver. Whereas here, the instantaneous channel behavior is known to the receiver, but the transmitter, instead of instantaneous channel condition, it has an average idea about the channel variation. So in this case, instantaneous channel variation is known for both the transmitter and the receiver, whereas here the receiver knows the instantaneous channel condition, whereas the transmitter knows an average of the channel variation. So, but this is easier when compared to this. It's difficult and this is easy. The problem is here it requires a slow feedback or calibration for the reciprocity. And third case, no CSI at the transmitter and full channel state information at receiver. So in all the three cases, we assume the receiver knows the instantaneous channel variation, but different amount of channel state information at the transmitter. So in the third case, the transmitter is not at all using any channel information for its transmission. So this is easier when compared to all these. So it does not require any calibration or it does not require any feedback. Then how the receiver comes to know about the channel state? So it is done by transmitting the training sequence and also by using blind estimation techniques. So using the channel training sequence, the channel can be estimated, or using blind channel estimation, the receiver comes to know about the instantaneous channel variation. So among the three, this is very easier because it does not require any feedback. Fourth one, It is noisy channel state information. So here also you don't have any information at the transmitter channel state information at the receiver. So in all these cases, we are assuming the full channel state information at the receiver. It means we assume the perfect knowledge of the channel is available at the receiver. But practically it is not so, because the receiver comes to know about the channel state by using the training sequence. While passing through the channel, the training sequence may get corrupted by the additive noise. So you have a erroneous knowledge, that is not perfect knowledge of the channel. So we are processing the received signal based on the observed channel. So there is a difference between observed channel and true channel. Actually, what is the channel? That is true channel. It is H true. And through our measurements, we are estimating the channel as observed channel. So this is the observed channel HOBS, and H2 is the actual channel. But since the training sequence is corrupted by noise, always there will be a difference between the observed channel and true channel. We are processing the received signal with the help of observed channel. And the last case, fifth case is no CSI at both transmitter and receiver. So among all the four, what we told is you can achieve the highest possible capacity when the instantaneous channel state is known for both the transmitter and receiver. It is also possible to increase the capacity even without making use of the channel state information. So in this case, the capacity increases linearly when we increase either the number of transmit antennas or number of receive antennas. Whereas here it is possible to increase the capacity by an amount So it is also possible to improve the capacity even without using the channel state information by an amount m tilde of 1 minus m tilde by TCOH. The TCOH is the coherence time, the time for which the channel remains constant. And the m tilde is the minimum of nt comma nr into floor of TCOH. Nt is the number of transmit antennas, nr is the number of receive antennas, and this is the previous nearest integer. TCOH is the previous nearest integer, because always the number of antennas should be an integer. This is the previous, the lower value of integer TCOH. So these are the 5 possible cases about the classification of algorithms that are used for Mimo system. The next topic is capacity in non-fading channels. In order to understand the Mimo systems, it is necessary for us to derive the equation for capacity. So we are going to start with the derivation for capacity in non-fading channels. So we are going to first consider a normal case. Normal case means we are going to consider one transmit antenna and one receive antenna, SISO, single input, single output case. And also we are not going to consider the fading, we are going to consider it as a non-fading channel. It means the only impairment of the channel is the additive noise. We are going to consider only noise, that is additive, and we are not going to consider non-fading. We are going to consider only noise, additive noise, and we are not going to consider the fading effect. So with this, we are going to start the derivation for capacity. The information theoretic capacity, that is ergodic capacity, which is given by the scientist Shannon. So we call it as Shannon capacity. C Shannon equal to log to the base 2 1 plus gamma into squared magnitude of h. The capacity, ergodic capacity for the SISO case with the noise, additive noise, and gamma is the SNR at the receiver for a given BR requirement, and h is the transfer function. It's a normalized transfer function from transmit antenna to receive antenna. So gamma is the signal to noise ratio at the receiver for a given BR requirement, and h is the normalized transfer function from transmit antenna to receive antenna. So from this expression, what we understand? So always we want higher capacity. So the capacity can be increased. The channel is not in our control. So only possibility is to increase the signal to noise ratio. So if we increase the signal to noise ratio, then the capacity will increase. But what is the function involved? The logarithm. So the increase in the SNR surely will increase the Shannon, but not Shannon capacity, but not significantly because of the logarithmic function involved. So a larger increase in the signal power or signal to noise ratio will result in a very small increase in the capacity. So increasing the signal to noise ratio is not a viable solution for increasing the capacity. So this is the single input, single output case with additive noise. This is the capacity equation for a single transmit antenna and a single receive antenna. A system is having single transmit antenna and single receive antenna. So increasing the signal to noise ratio will increase the capacity but not significantly. The next is Mimo case. H is equal to W sigma and U pseudo inverse. So for Mimo case, H is going to be a matrix. So H is the channel matrix. The dimension is based on the number of transmit antennas and number of receive antennas. The rows and columns are determined by the number of transmit antennas and receive antennas. So always we are interested in the diagonal elements in order to get back the transmitted signal. So we are going to decompose the channel matrix using singular value decomposition. So in generally, the number of transmit antennas and number of receive antennas will not be of same size. If it is same, then we can write H and H inverse, but this is not the case. So we are going for the singular value decomposition in order to get the diagonal elements. So H is written as W into sigma into U pseudo inverse, where the sigma is a matrix, it is a diagonal matrix. Sigma is a diagonal matrix whose the elements are eigenvalues or singular values, and W is a unitary matrix and U is also a unitary matrix. This dagger symbol represents a pseudo inverse because the number of rows and columns are not same. So this is pseudo inverse. So by doing this, we will get back the diagonal element. So W and U are unitary matrices. They are the left and right eigenvectors or signal vectors, singular vectors. And the received signal is represented by R is equal to, so the received signal is represented as Hs plus N. H is the channel matrix, S is the transmitted data, and N represents the additive wide Gaussian noise. And now we are going to substitute the decomposition of H here. So instead of H, I am going to substitute W sigma U pseudo inverse. So W sigma U pseudo inverse S plus M. So this is the received signal. Next is the received signal and the transmitted signal. So I am going to multiply the transmitted signal S with the unitary matrix U, and the received signal R is multiplied by another unitary matrix W, W pseudo inverse. So by doing this, so this will give a similarity matrix, that's identity matrix. So I can write this as R tilde equal to sigma S tilde plus N tilde. This is going to be the diagonal matrix whose elements are eigenvalues or singular values. That is what we are interested in. And this N and N tilde, they have the same statistical characteristics as this W is the unitary matrix. So the statistical characteristics are preferred. So N and N tilde are having the same statistical characteristics, and sigma is the diagonal matrix whose elements are the eigenvalues or singular values. Sigma is the diagonal matrix whose entries are the eigenvalues or singular values, and the number of non-zero values are the singular values, and they are going to determine the rank RH. The rank of the matrix is represented by RH, and the entries are represented by sigma k. It is a matrix and whose elements entries are represented by sigma k, and the number of non-zero sigma k is the rank of the matrix. So if all the diagonal elements are non-zero, then the matrix is said to have full rank RH. So RH tells you the number of non-zero singular values, and if they are, if all the numbers are non-zero, it means each non-zero value corresponds to one channel. So you have several parallel channels. All the channels are parallel. So the non-zero elements corresponds to eigen mode or parallel channels. So for a parallel channel, the total capacity is the sum of individual channels capacity. So to find out the total capacity, we are going to add up, we are going to sum up all the capacities of each and every individual eigen mode, that is channel, parallel channel. So totally how many parallel channels we have? We have RH, which is the rank, non-zero entry of the diagonal matrix. So RH is the rank. We have RH parallel channels. So total capacity is just the sum of all the individual capacities. So RH is the rank of the matrix, and Pk is the kth channel power, power of the kth channel, and sigma n is the variance. This term corresponds to variance of noise, and this is a factor which is going to determine the power transmitted through that particular kth channel. So this equation for capacity can be rewritten as this, where INR is the identity matrix of dimension NR by NR. What is NR? NR is the number of receive antennas. So I subscript NR is the identity matrix of dimension NR by NR, and gamma dash is the mean SNR, and NT is the number of transmit antennas, H is the channel matrix, and RSS is the autocorrelation matrix. RSS is the autocorrelation matrix, correlation matrix whose entries are the sigma k, which is going to determine the power carried in each channel. And we are going to assume the uncorrelated data is transmitted from each and every antenna, so that we can make the assumption of parallel channels. And from this equation we can understand the capacity increases linearly as the number of transmit antennas, receive antennas increases, so the capacity also increases. The capacity is proportional to minimum of NT, NR and NS. Whereas in the previous case it is single input, single output. So increase in the power does not reflect in the increase in the capacity, whereas here the capacity can be improved by increasing the number of either transmit or receive antennas. So here capacity is proportional or it is linear with increase in the number of transmit or receive antennas. So here we are going to consider two cases based on the amount of channel state information required. In both the cases we are going to assume the receiver has the perfect knowledge about the channel. Only the difference is at the transmitter, full CSI at the transmitter, or no CSI at the transmitter. So in both the cases, we are assuming the receiver is having full channel state information, whereas transmitter either will have full channel state information or no channel state information. So first case is no channel state information at the transmitter and full channel state information at the receiver. So we are going to consider the uncorrelated data stream transmission. So we are not putting this H or SS. So we are going to consider uncorrelated data stream transmission, and also since no channel state information is available at the transmitter, it is better to distribute the power equally among all the parallel channels. So equal power is allocated for all the parallel channels, and we are going to assume uncorrelated data transmission. In that case, the capacity of the No CSI at transmitter and full CSI at receiver cases derived as log of INR plus gamma dash by NT H into H pseudo inverse, where gamma dash is the mean SNR, NT is the number of transmit antennas, and INR is the identity matrix of dimension NR by NR, H is the transfer function of the channel. Now we know the capacity increases linearly with minimum of NT, NR, NS. Now we are going to assume a sufficiently large value of NS. In that case, the capacity becomes independent of NS and depends only on NT and NR. It depends only on the number of transmit antennas and number of receive antennas. Now we are going to consider a special case where the number of transmit antenna and number of receive antenna are equal to a value n. That is, the channel matrix becomes a square matrix. Now case 1, how about the entries? If the entries of the channel matrix are all identical, if all the entries of the channel matrix is same, that is H11 equal to H12 up to HNN, and this is possible, all the entries of the channel matrix, that is individual transfer functions, can be identical only when the antenna elements are spaced very close to each other. In that case, the capacity of the Mimo system is written as log 2 into 1, log 2 of 1 plus n into gamma dash. It means the signal to noise ratio is increased by times n. N times the signal to noise ratio increases when compared to the case of single input, single output, one transmit antenna and one receive antenna. So in this case, the first case, if all the entries are same, because of the closer spacing between the antenna elements, the SNR increases by an amount n. The next case, the entries are of different values. The entries are different, and since they are different, all the diagonal elements are non-zero and the rank of the matrix is full. It is a full rank matrix. The channel becomes a full rank matrix, and when it is possible, when all the entries are different, when the spacing between the antenna elements are sufficiently large, then the entries of the transfer function will be different. So in that case, the capacity of the Mimo system is derived as n into log 2 of 1 plus gamma dash. So in this case, the capacity increases linearly with the number of antennas. So compared to this, the SNR is same, whereas the capacity increases linearly with the number of antennas. So if number of antennas increase, in this case, it's a possible for increasing the capacity. The third case is parallel transmission. If we consider parallel transmission, the capacity is derived as n log to 1 plus gamma dash by n. So here also the capacity increases linearly as that of second case n. In addition to that, the SNR requirement is reduced by a factor n. So SNR requirement reduces by a factor n. At the same time, capacity increases by a factor n. So this is about the capacity under no CSI at the transmitter and full CSI at the receiver. So if the transmitter is not having knowledge about the channel, it is better to allocate equal power among all the parallel channels. The second case is full CSI at the transmitter and at the receiver. Oh, no. So the graph shows the improvement in the capacity through the number of antennas. So the number of antennas are varied from 1 to 10, and we are comparing the three different cases: identical transfer function,